It is my pleasure to introduce the next speaker this afternoon. Is Cristina Lizana, and he's talking about invariance of entropy for mass isotopic to Anosov.
So thank you, Leonardo. Well, first I would like to thank the organizer. It's a great pleasure to be here in the Magnet at IMPA and celebrating the anniversary, the birthday of Jacob. So I'm going to talk about, this is a joint work with Enrique Pujas, a child of, a son of Jacob, Carlos Vázquez also, a son of Jacob, and Pablo Carrasco and myself. So this is a joint work that, let me put first the setting. So we are going to set up our work in C1 diffeo, okay, in a compact boundary manifold. And as you saw in the title of the work, the idea, if you have a class, you have a map, and you look at the isotopic class of this, and you are trying to show the simple model in this class. So, of course, simplicity, it could be relative that, about what you are looking for. So we decided the simplicity in terms of topological entropy, so the less complexity of the orbits. And since this is something new, we are going to work in a class that we know something about this. So we are going to work in a setting of partially hyperbolic diffeomorphisms that are isotopic to an Anosov. So to motivate the problem, in dimension 2, we can look at the Nielsen-Thorson classification. So if you take a diffeomorphism, there is a homotopic diffeomorphism that has to be in one of these three types. So it's identity for some P, or it's a pseudo-Anosov, or lives invariance on finite a set of closed simple curves. So what would be the simplest model in each of these classes? So for the first one, you know that could be a periodic map, and you have that the entropy is 0. For the second, for the pseudo-Anosov case, Fatih should prove this result, and they show that the simplest model is the pseudo-Anosov linear, and then the entropy should be larger or equal to the original one. And the third case, you can decompose and get the other two cases before. So that is in dimension 2. So the question is, what happened for higher dimension? So the natural question is, can we characterize these minimizers, or if we can give some sufficient condition to find this minimality, this representative diffeomorphism in the class that has the less complexity in the term of topological entropy. So what is derived from Anosov? It's just a diffeo that is isotopic to an Anosov. Okay? So that is the setting we are working. And in any dimension. And the classical example of Magnet, you have, you start with an Anosov one, you have a fixed point that is a saddle point, and you make a pitchfork bifurcation in the weakest direction. You see in the draw is in green. You make a bifurcation, and this point open in an interval. So what happened with this example? You have a very good behavior in the central bundle. I mean, when you iterate this segment, the bounded of the length of the segment remains always bounded. And you can prove, actually, that the entropy of the isotopic is exactly the same of the initial one. So that is an example, but there are some general results of Bussi, Fisher, Vasquez, and Zambarino, and Ures, but they use strongly that the central dimension is 1. So they got that if you have a DA with central bundle one-dimensional, then the entropy remains the same. So the natural question is, what happens if the central bundle has higher dimension? Can we obtain similar results? So that is the goal of this talk, actually, the main goal. And we prove, actually, that you can get a similar result if you have a DA, partially hyperbolic. Remember that I mean partially hyperbolic. If you look at the tangent bundle, you have a behavior like this. So you have an expanding and a contracting uniform, but this one is not expanding and contracting uniformly. Okay? So this map is isotopic to an Anosov. And if we require, we give these two conditions, that the stable and unstable foliation are quasi-isometric, and the central bundle is simple, then the entropy remains the same. So let us talk a little bit about the hypothesis, okay? So the quasi-isometric property is basically if you have the foliation and you look the distance along the foliation, it's almost the same in the manifold. So you have a foliation that is well-behaved. It's not doing something so crazy. So you have what we call a control geometry. And the central bundle, to be simple, is basically, remember that this one has dimension. The dimension is larger or equal to, so you decompose in a direct sum of one-dimensional subbundles. And each of these integrate to foliation that are quasi-isometric. So that's what I mean for the simplicity condition. So the question is, okay, what happens if you don't have this condition, the simplicity condition? So we can show an example that is robustly transitive, and the entropy is larger. You can do very larger than the initial one. And the example that we contract, I'm going to talk about, this one, G, is partially hyperbolic, is isotopic to the Anosov, but the central dimension has not this simple condition, the simplicity condition. So you cannot decompose in a direct sum of one-dimensional subbundles. So coming back to the hypothesis, I said, okay, you ask to the unstable, stable foliation to be quasi-isometric. So recalling the Briggs result, we have that if you had this condition about the stable and unstable foliation, you get the central bundle is uniquely integrable. So that is a very strong result. It's not easy, and it's going to be very useful for what we are doing. And the foliation are, they are going to be actually quasi-isometric. So Andy Hammerling, he proved that if you have this quasi-isometric condition, then you have a sort of global product structure. So what I mean for this, you have the center unstable manifold, and you have the stable manifold here. They intersect just in one point. So that is what I'm saying in this condition. And the same happens for the center stable and the unstable foliation. Okay? And the center foliation is homeomorphic, are all homeomorphic, and the foliation are quasi-isometric, as I said. So they behave very, very nice. So the idea of the proof, I put this 4 step. I'm going to talk about this. So the idea is to prove first, the first step, so if you take a point, you look at the class. So I should mention before, if you have F isotopic to Anosov, using lemma, the Frank's lemma, you can construct a semi-conjugation between F and A. So you have a semi-conjugation here. And what I mean for the class of X is you take a point here, and you look at the pre-image of this point. So the semi-conjugation has point where the pre-image is 1 point, or it could open in something else. Okay? In the example of Magnet, for instance, the semi-conjugation, it's always injective, it's 1-to-1, except in the point where you open to the interval. Okay? So this is what I denoting like this. Okay? So the idea, the first step, is to show that given any point, you look at the class, and all the points in the class belong to the same central leaf. So the idea is the following. You pick 2 points here, and you look at the center unstable manifold of one of these, and suppose that the other point is outside this leaf. So assume that Z is here, and you know, remember that I said about the global product structure, you had the stable foliation of Z is going to intersect the center unstable foliation. So you have a point here. Remember that Z is someplace here. And if you are assuming that Z is outside, you can look at the backward iterates. So the iterate of Z and W, they start getting far away exponentially. Okay? But this distance here, the distance from here to here, is bounded. Why is bounded? Because this conjugation, you can get at bounded distance of the identity. So the diameter of this class is bounded. It's uniform bounded in all for every point. So when you iterate these 2 points, you look at the forward orbits, they remain always bounded. So what happened? The distance between W and Z prime is larger than the distance of this. So you can have this simple inequality here. So you know that this term is bounded. And you are assuming W is in the center unstable foliation. So we can work here with the backward iterate, if you want, for the past. So what happened? That this one is going to contract. He's going to contract, probably. We don't know. But it cannot contract stronger than the contraction you have here. So if you are working for the past, this exponentially expand. This cannot be cannot expand larger than this one, so you get a contradiction. Okay? So what you get actually is that this point Z has to belong to the center unstable foliation of Z prime. So using an analogous argument, you prove also that Z has to be in the center stable foliation of Z prime. So finally you get that Z has to be in the center foliation of Z prime. So that proved the first step. So what we are saying, you take any point, you look at the class, all the points in the class belong to the center foliation. But we have something stronger. The second step, you are saying the following. So you have Z and Z prime. They both goes to H, to X by H. And they are in the same one-dimensional center leaf. Remember that we are assuming the simplicity condition. And we want to show that all the points here in this segment actually by H goes to X. That is what I'm saying in the second claim. So if you had 2 points that are in the same class, all the points in between are in the same class. So the idea here, again, we use strongly the quasi-isometric hypothesis. So if you choose any point here, W, and you compare the distance from W to Z and all the iterates, you can prove that actually they are going to be bounded by the distance between the iterates of Z and Z prime. And when you use that the map is isotopic, you get this semi-conjugation. You are showing essentially that when you look at this point down there, so assume that you have this point here, the iterates by the Anosov, they remain at bounding distance to the iterate of X. So you have this one remains bounded. Okay? But now you have the dynamics in the basis is an Anosov. And if the iterates are all bounded, the only way is that this point has to coincide with X. Remember that we have this one is hyperbolic. So for any point that you take in this segment, they go by the semi-conjugation to this point X. So that would prove the second step. So remember that the central bundle is dimension larger than 2. So, okay, you have a point, you look at the class, it can open in a segment. But you have now more degree for moving. So what happened with the other center bundle? Remember that we have here that the center bundle is decomposed in one-dimensional subbundles. Each of these are one-dimensional. So if you open in a segment, that was step 2, everything inside this segment it goes to this, it's in the same class. And what happens now if you have a point like this, for instance? So, step 3, you have 2 points, Z and Z prime, in the same class, but they are not in the same one-dimensional foliation. So you have one foliation here goes through Z, and the other foliation going through Z prime. Let's call this 1, and this W2. And we have to show that this point of intersection belongs to the point X, to the class. If we prove that this point belongs to the class, using the step before, we had that all this segment belongs to the class, this segment belongs to the class, and now we do the following. You look at the W1 Z prime, W2 Z. For the same argument, you have that this point belongs to the X class. So you have actually that all the points inside here, if you foliate this box, this rectangle, that is what we are calling rectangle here, all the points inside actually belong to the same class. So I repeat the argument. You have these 2 points in the same class. We first prove that this point actually is in this class, and using the same argument, you prove that all the points inside belong to the class, to the same class. So what is the idea? To prove that this point here belongs to the class. Okay. So basically, again, you have to use the quasi-symmetry and the semi-conjugation, that you have the class is at bounded diameter. So if you iterate this point, the forward orbit remains about the distance. And this point, we are assuming, remember that we are assuming that each of these subbundles are foliated, and each of these foliations are quasi-isometric, so you have a good behavior. And you are working in a compact manifold. So you iterate, and you have that the distance of this point has to be at bounded distance of the iterate of this point, and also the iterate of this point. So this cannot grow infinitely, and you get some control on the angle of this when you start iterating, okay? So you prove that actually this point belongs to the class, okay? And you can start with a certain distance here, a small distance, because the problem that could be that this intersection could be empty, but it's not empty, okay? And because of this kind of global product structure in the center bundle. So if you have the central bundle is dimension k, you can obtain the class could be a segment, a two-dimensional rectangle like this, and you can go with higher dimensions. So it's the same idea. So if you have this basis that belong to the same class, and now you look, you have a point outside that is also in the same class, and you look at this segment, you can construct a higher dimension rectangle that also every point inside this class, in this rectangle, belong to the same class. So what we are saying in the third step basically is that you have a very controlled geometry of the class. So you have that each of these class decompose in a finite number of rectangle, could be of any dimension from 1 to k. But the geometry is going to be nice. Nice in the same sense that we were saying for my example. So if you iterate, the diameter of these boxes remains bounded, and you can finally say that you have a finite union. Each of these class is a finite union of some of these sets, and you prove that actually they are not going to add entropy. So finally, you prove that the only set that you can probably addition some entropy are this kind of set, but you have this contour geometry, so you get that actually they are not adding anything to the entropy. So you got finally that the entropy remains the same. Okay? So it's not hard to construct an example of this that represent this theorem. Okay? You start, for instance, with an Anosov, and in the stable foliation, you do like a derived from Anosov, and in the unstable direction, you do another derived from Anosov. So you are opening in something dimension 2. And they have all the properties in the theory. And you can do this in a robust way. Okay? So remember what I said. If you don't have the simplicity condition, you can construct an example that is actually with a topological entropy larger than the initial. So how we do this construction? So consider alpha a totally real piece of number, and consider the companion matrix. So this matrix, it's a linear Anosov, and decompose in one-dimensional subbundles. You have a one-dimensional unstable, and the other are all contracting. And then you can prove easily that the entropy is exactly the log of the largest eigenvalue. And you consider a fixed point of this linear Anosov. You consider a small neighborhood where you are going to do a perturbation just in the center bundle. So you have, for the initial, the center bundle was a weak stable and something that was a little bit more stable, more contracting. And you can do a deformation just here in these two bundles, and you get a new map, a new diffeomorphism, that this bundle is two-dimensional and you cannot decompose. So you get the real eigenvalues, you become complex. That is what we are doing. So you consider this map is isotopic to the initial. It's partially hyperbolic. Here, the center bundle is two-dimensional, and you cannot decompose. This, the stable, unstable, both are one-dimensional. Okay? And since it is isotopic to the initial, you have easily that the entropy is larger or equal to the initial. Okay? So now we are going to do a second deformation. Okay? You remember that you had this fixed point. And we are going to do a Tensby-Bronsey deformation. And I'm going to explain what I mean for that. And this map is, the new map is isotopic to the initial. It's partially hyperbolic. The stable, unstable, both are one-dimensional. The center is two-dimensional, but is indecomposable. And the entropy of this map is going to be larger, strictly, than A. Okay? And is robustly transitive. So why we add this robustly transitive condition? Because you can construct this kind of example artificially, but the idea is that the dynamics is not concentrated just in one place. So you want everything mixing. Everything is going to be just one basic set. So how is this deformation? So you have, remember that the central bundle, you have a complex eigenvalue, that the central bundle was undecomposable. And now you can open, in a small neighborhood, you can open and start doing a deformation, a continuous deformation, to get here inside, in each level, until you get a horseshoe. Okay? So that is the dynamic in the center bundle in a small neighborhood of the fixed point. So when you do a zoom, you are having this. Outside behaves the same. So if you look now in the dynamics, you forget about the stable, okay? Because we are in fourth dimension. I cannot draw in fourth dimension. So I just look at the center. The center is here, and the unstable direction. So what you are doing in each level, you are doing the deformation until you get the horseshoe. But this construction that we have done, we preserve that the center bundle is, the center foliation is dense, is minimal actually, okay? So we got an isotopic map to the initial one that inside this small neighborhood, you get a horseshoe. Outside is the same as the linear, okay? And has these three properties. So the first one, you are saying the same, this. So in the first property, you are saying if you pick an open set U and you choose, let's change the name, V1, and you choose an interval, unstable interval. Here, this is unstable interval. For the first property, you have, there is a point. There is a point here that has the property, when you look at the iterates of this, it remains in the good region. What I mean for the good region, they avoid U, that is the support of the perturbation. Okay? So the forward orbit of this point at some time started going in the expanding region, actually. And the second property, since the perturbation we done is we don't destroy the center foliation, it has the same property as the initial, so it's minimum, okay? And the last property is going to guarantee for us the transitivity. So how we do the argument to prove that this is transitive? So you start with V1, and you have V2, another open set, and you want to show that for some n, this has to intercept V2. But remember that the forward orbit of this point is in the expanding region. So if you choose a small ball here, and you look at the behavior of this ball, probably it's going to be distorted, but in some moment, the internal radius is going to grow. That is what is saying the third property. So you have probably it's very distorted, but the internal radius, so you can put inside a ball with a radius r. So this r depends on the open set. So for this set, V2, there exists some r, having the property that the central, let's see, the center, oh yeah, epsilon, with radius r is contained in the image of this disk, where this r is sufficiently small to get this ball here inside V1. But you know that this set, for some n, is going to intercept V2. So you got finally that V2 is actually intersecting some iterate of V1. And all this construction is robust. So you get an open class of example where they are all transitive, and the entropy is doing some calculation. I'm not going to show you because it's technical. You have to do the calculus. It's larger to the initial one. So you got an open class of example where you don't have this simplicity condition, and the entropy grows. Okay? So I want to emphasize that in the theorem A, the example, you can construct an example where actually the center bundle is not hyperbolic. So you don't have a uniform behavior, okay? So actually you are in the setting of partially hyperbolic. So that is more or less the idea of this result, okay? And I left to the end to talk about Jacob. And when Lorenzo sent me the invitation to speak here, I started doing some search, and I started having some flashback from when I was a child, because I always hearing my father is mathematician, and he always talked about when Jacob was in Venezuela. He was twice in Venezuela, and actually one of these occasions it was for receiving the TWAS prize in Caracas. And I was doing a search to find a picture, and I couldn't find anything until yesterday. It was a happy coincidence that the president of the TWAS, he put some pics when Jacob was in Caracas in 1919 to receive the TWAS prize. And I mean, at that time, I was just shy. I didn't have idea what we were receiving in Venezuela. And now I could realize that it was such a big conference. It was the general conference of TWAS. And it was such an honor to have Jacob receiving this prize in Venezuela, actually. And well, I decided to study math. And another happy coincidence was that when I was almost finishing my undergraduate, Leonardo came to Merida. And I decided to work with him. And I was trying to see what I was doing after my undergraduate. I remember that at that time I was thinking to go to USA. And Leonardo said, well, you know, there is a place in Brazil called IMPA, and maybe you can go there, you can apply there. And I said, okay, let's try, why not? And I did the master with Leonardo, and applied to come to IMPA, and I was accepted. And also, another happy coincidence is that my fellowship for the PhD was a TWAS fellowship. That is also one of the Jacob contributions. So it's a chain of happy coincidence. So I came to Brazil. I remember that I did the hyperbolic dynamics course with Marcelo, but then I was preparing the qualify. And another happy coincidence was Jacob was teaching that semester, and I entered to get the ideas he was saying. I mean, it was, until today, I remember the proof of the lambda lemma he was saying. It was so nice, you see. You can view the draw and understand the proof. That is so amazing, and it's so inspiring. And then I didn't was to the 60, but I was in the 70. I was still a PhD student, so I put some picture of the Jacob sons, some pictures of the grandchilds. So one of the most special things that all the picture, he looks so happy. I mean, all the picture, he's smiling. And a couple of months later, I defended my thesis. And another happy coincidence, Jacob was in my jury. And you see, he's always smiling. I remember that was in the middle of the World Soccer Cup. So nobody wants it. It was a Brazil game, so that it was hard to have the jury. And of course, when you are defending your thesis, you are so nervous. And was the time for the question, and Jacob said, okay, what are you planning to do after this? So I was thinking in mathematics, you know, you say, no, I'm trying to do this and that. No, I mean, what are you planning to do with your life? And I said, well, I plan to come back to Venezuela and try to do what all the people here taught me. And certainly, Jacob, he touched us in many ways, in different ways, that we cannot realize how all connect. And I just wish to Jacob a lot of many, many years with us. You are a very nice person, academical and as a person, and I want to wish you Feliz Aniversario.
Any questions? Okay, let's acknowledge Cristina for his talk. Please, again.